properties of activated carbon. And we have various metals such as aluminum, magnesium, zinc, and iron to improve upon the adsorption properties of activated carbon. However, iron is generally preferred to remove arsenate in water because it has a superior attraction to arsenate. Iron is readily available and it is also cheap. And when it comes to the iron attachment method, there are two main methods we use to attach iron to a fabric or to our activated carbon. The first is the impregnation method, whereby we put our biomass in an iron solution before carbonization and we carbonize or activate afterwards. And the second method is a co-precipitation method, whereby we put our activated carbon in an iron solution and we increase the pH of the solution with a base so that iron precipitates would form onto our adsorbents. I know we are talking about iron and there are so many concerns about potential iron leaching. So one thing we also want to do is to ensure that our adsorbents are safe for use. So for our main objective today, we are going to see how to enhance arsenate removal in synthetic stormwater using iron modified adsorbents. And for our specific objectives, we are going to quantify the total iron loading and the stability of the iron. Secondly, we'll also look at the surface characteristics of BC, AB, GAC, and ACF. We'll also evaluate the performance of our raw materials for arsenate removal, and finally look at arsenate removal performance of our iron modified adsorbents. So with our experimental design, we are going to use 10 millimolar KCl to maintain constant ionic strength because KCl can also mimic our stormwater as well. Secondly, all our arsenate removal experiments was carried out as pH 7 and all our experiments were also carried out in triplicates. And for our adsorbent preparation, for our granular adsorbents, we sieved them into uniform sizes between 300 micrometer and 425 micrometer. We washed them with deionized water and dried in an oven at 100 degrees Celsius for 24 hours. And for our fabric materials, we cut them into strips. They also underwent a washing procedure with deionized water, and we dried them at 100 degrees Celsius for 24 hours. So for our first objective, we wanted to quantify the total iron loading and the stability of the iron coating. So how did we go about this? We did the co-precipitation method, whereby we had our ferric chloride dissolved in the ionized water. Once we had that, we put our adsorbents into the iron solution and we increased the pH to 9.5 using a base, that's sodium hydroxide. Once we're done with the iron precipitation method, we washed the adsorbent with deionized water, we dried it in an oven for 24 hours, and then we cured at 300 degrees Celsius for 1 hour. So once we're done with this, to quantify how much iron we had on our material, we put our adsorbents into ferric chloride. We put our adsorbent into hydrochloric acid. The reason why we use hydrochloric acid is because the acid is going to dissolve all our attached iron into our solution. So we did 2 washes, and then we prepared our iron solutions and our standard curves using our hydrochloric acid. There were 3 main reagents we used for this quantification. The first reagent was a hydrolasmine, which converts Fe3 plus to Fe2 We also had sodium acetate, which acts as a buffer. And finally, we had a phelanthroline, which reacts with Fe2 to form a bright orange complex. Also for our iron leaching quantification, we went through the same process, except that we had our background solution was KCl because our arsenate removal experiment was carried out in KCl at pH 7. And we also prepared our iron concentrations using the 10 millimolar KCl. So once we had our solutions, the first image on our left just gives us an idea how Fen reacts with arsenates to form a bright orange complex. We measured the absorbance of our solutions using the thermoscientific spectrophotometer at a wavelength of 510 Newton meters. So looking at the results, on our x-axis, we can see our adsorbents, The blue color signifies unmodified adsorbents, and the orange color signifies ion modified adsorbents. And on the y-axis, we have the ion concentration in milligram per gram. So before ion modification, we can see negligible amounts of ion present in our material. However, after ion modification, AB had the highest ion loading, followed by GAC, ACF, and biochar. So this confirms that we had ion loaded onto our adsorbents. And for the ion leaching test, the EPA recommends having a maximum ion contaminant in water capped at 0.3 milligram per liter. And as you can see, with all our adsorbents, we didn't detect any form of leaching. So our adsorbents are very, very stable in solution. So for our second objective, we also wanted to evaluate the surface characteristics of all our adsorbents. So the first thing we did was the proximate analysis. And this analysis gives us the moisture, volatile matter, and ash content available in our adsorbent. And the reason why we want to look for these volatiles, moisture, and ash percentages is to find our fixed carbon in our adsorbent. Since we are using carbon-based adsorbent, it's very, very prudent to find out how much carbon we have remaining after we've taken out moisture, ash, and volatile matter. So we carried out our approximate analysis using these ASTM standards here. Also for the ultimate analysis, that was another characterization step we took, and this is to basically find out the elemental carbon, elemental hydrogen, and elemental nitrogen present in our adsorbent. This was done using the Perkin analyzer. We also wanted to carry out porosity analysis, but before we did that, we did a degassing step to make sure all our adsorbents were dry and didn't contain any form of moisture or volatile matter. So we carried out this degassing step with our micrometric sample degas system at 300 degrees Celsius in an inert atmosphere for 1 hour. And for our porosity analysis, we used the micrometric TriStar analyzer, and basically this equipment is able to give us the surface area, pore diameter, pore volume, and absorption isotherms of our material. This analysis was done using nitrogen gas, and we also had a dewar containing liquid nitrogen at a temperature of 77 Kelvin. For our pore size distribution to see how the pores are distributed within our material, we used CO2 gas for our analysis, and our dewar contained crushed ice at 273 Kelvin. Another characterization step we did was the point of zero charge, and this is basically one method to find out if our adsorbent has any form of charges, whether positive or negative. And we use the pH drift technique to do this. So we also had our same KCl background solution, and we had our solutions in pH ranging from 2 to 12, and we adjusted the pH with an acid or a base to reach these pHs. We put our adsorbent in the solution for 24 hours on a tube rotator, and then at the end of the day, we found a change in pH. And once we had this change in pH, we found a point of zero charge, which was the intersection between our initial pH and our change in pH. So for our results for our approximate analysis, generally, carbon adsorbents have low moisture content below 20%. They also have ash contents less than 10%, and they generally have volatile matter as high as 30%, but once they are activated, their volatile matter can be as low as 10%. And generally, carbon adsorbents have a carbon content above 70%. So for our biochar, we can see our moisture content was a little bit small, and we had a lot of volatile matter, about 16%. After activating biochar, that is an AB here, we had an increase in our moisture content. And this increase in our moisture content just gives us an indication that some pores have been created, thereby the material has even started attracting moisture in the environment. The volatile matter activated biochar AB also dropped from 16% to 6.31%. And this drop in volatile matter also indicates that volatile matter was lost during the activation process. So all our adsorbents, as we can see, are high carbon material because they have a carbon percentage more than 70%. So for our ultimate analysis, we did this to also confirm the elemental carbon in our materials. That was what was of interest to us since we were looking at carbon materials. And this also was more than 70%, which confirms that our materials have a highly developed carbon structure. Our nitrogen and hydrogen percentages were relatively low, less than 5%, signifying that our adsorbents are stable and the carbon structure has been developed. With our isotherm graphs, the IPAC classifies isotherm graphs in 6 main ways. We have the type 1 to type 6 isotherm graphs. And when we say the type 1 isotherm graphs, they are basically characterized by a steep adsorbed intake of nitrogen and then it plateaus eventually. So looking at our isotherm graphs, we can clearly see that this is a type 1 isotherm graph. And type 1 isotherm graphs are basically used to describe materials that are also very microporous in nature. That means they have pore diameters less than 2 nanometers. So let's go through our isotherm graph. On our x-axis, we have our relative pressure from 0 to 1, and we have our quantity absorbed of nitrogen from 0 to 350. So first and foremost, for our raw material, we wanted to find out the effect of ion modification on our adsorbents. So for biochar, which is characterized by a red line, we had some nitrogen uptake. However, after modifying it with ion, we realized the quantity of nitrogen absorbed increased. This increase in nitrogen tells us that the surface characteristics of biochar has increased. It probably has an increase in surface area or an increase in pore volume. And also for activated biochar, the nitrogen intake for activated biochar and ion modified biochar was fairly the same, signifying that ion attachments did not really do anything to our adsorbents. For GAC, we saw a reduction after ion modification, and this signifies that the pores of our material could have been blocked by the ion precipitates. And we also had a similar situation with our activated carbon felt, which saw a reduction in the nitrogen absorbed. So looking at our next table, we can clearly see for biochar that our surface area increased after ion modification. Our pore volume and our micropore volume also increased after ion modification. So we're trying to understand why this increase happened, and current studies have shown that iron chloride is now being used as an activating agent to chemically activate carbon adsorbents. And we can also say that our biochar underwent chemical activation after ion attachments because of the heat treatments that we also took. And secondly, our biochar had volatile matter present, that was about 16%, which meant that all that volatile matter could have been lost to also open up the pores of the material, which we can see in its surface area and micropore volume. Activated biochar and ion biochar had the surface area fairly same. Its pore volume and micropore volume didn't also change much. For GAC and ion GAC, after ion modification, we can see a reduction in our surface area. We can also see a reduction in our pore volume and in our micropore volume. We had a similar story for activated carbon felts, whereby after ion modification, our surface area also reduced and our micropore area also reduced. Generally looking at our pore diameter, we can see that all our materials are microporous because that is characterized by the pore diameter being less than 2 nanometers. And also we can confirm that with our microporosity, which confirms that all our materials were highly microporous. So to further understand what was going on in the pores, we carried out a pore size distribution. And this was basically done to see how our pores widths look after ion modification. So starting with the raw biochar, we can see on our x-axis pore width and pore volume on our y-axis. Before ion modification, biochar had a single pore volume, and after ion modification, we can see additional pores being created even here as well. And this indeed confirms that chemical activation indeed took place, and thereby improving the surface characteristics, surface area, and pore volume of biochar. For activated biochar, our pore volumes and our pore width was overlapping. For our ion GAC, we can see our pore width closing after ion modification because we had bigger widths. And this also confirms that indeed ion precipitation did block some of the pores of GAC. And we also saw something similar for ACF, whereby we had a broad pore width, which is characterized by the blue line. But for ion ACF, after ion modification, our pore width reduced. This also confirms that the pores were blocked after ion modification. So to understand what was going on with ACF, we had a look at our entire pore width. That was the maximum our equipment could give us. And the pore volume and pore width was still overlapping. So since we can't see where the ion is, we do think the ion was also formed outside the macroporous region, which is greater than 100 nanometers. So the results for our point of zero charge. This was basically done to tell us the charges present on our absorbent, whether they are positive or negative. An absorbent has a negative surface charge if its pH is greater than the point of zero charge. And it has a positive surface if its pH is less than the point of zero charge. So for our experiment, our arsenic experiment was carried out at pH of 7. So as we can see, biochar, which is the blue color, has a pH which is less than a point of, has a point of zero charge, which is less than a pH. So biochar has a negative surface charge. However, for the rest of our adsorbents, they have a positive surface charge because this pH was less than the point of zero charge for our remaining adsorbents. So biochar had a negative surface charge and our remaining adsorbent had a positive surface charge. The reason why we looked at the surface charge was because arsenate on its own at pH 7 has a negative charge. So we think an adsorbent having a positive charge should be able to attract arsenate. So for our third and fourth objective, we wanted to evaluate the removal performance of our ion modified adsorbents and our non-modified adsorbents. So we did two main experimental works. First was the adsorption kinetics, and this is done to tell us how fast arsenate is trapped into our adsorbent. So we had a known concentration of arsenate solution. We put our adsorbent in the solution, and we took samples at various time intervals from 30 minutes up to 48 hours. And then once we're done with that, we had two kinetic models, the pseudo first order and the pseudo second order, to do our modeling. So the pseudo first order assumes that our adsorption process is a physical adsorption process, and the pseudo second order assumes that we are looking at a chemical absorption process. So for the adsorption capacity, that was also done to find out how much arsenate our adsorbents can hold. And we carried this out at various concentrations from 5 milligram per liter to 100 milligram per liter, where we put our adsorbents in our solution and we left it in the rotators until equilibrium at 48 hours. We also used the Langmuir model and the Friedrich model for our absorption capacity modeling. The Langmuir model generally assumes a monolayer adsorption, saying that absorption is happening on a homogeneous surface, our adsorbent has a homogeneous surface. And the Friedrich model assumes a multi-layer adsorption on a heterogeneous surface, meaning the adsorbent surface has various binding points and various binding energies. These are the nonlinear models we used, and we did this modeling in GraphPad Prism. So for our arsenate quantification, we used the ascorbic acid method, and the standard method we used was a 4500 PE. So with this method, we had our arsenate solution, and we added a combined solution made up of sulfuric acid, potassium tartrate, ammonium molybdate, and ascorbic acid. Arsenate reacts with molybdate to form a deep blue color. Our incubation was 1 hour for the color to fully develop, and we used our spectrophotometer to measure our wavelength at 880 nanometer. So this just gives us an idea of how acinates react with molybdates to form a deep blue color. So for our results, as we can see for our unmodified adsorbents, we have a time in hours on our x-axis, and we have a capacity with time on our y-axis. So starting with the biochar, we have our data points classified by the black dots. The red dot is a PFO, and the blue dot is a PSO. So from this, we can see that the PSO model best fits our data. For activated biochar, there was an overlap between our PFO and our PSO. We also had a similar situation here with Fe, or with granular activated carbon, GAC. And for ACF, the PSO model best fits our data. For our ion modified adsorbents, we also had a similar situation where the PFO and the PSO models were overlapping, and it was also overlapping for our activated biochar as well. However, for our ion modified GAC, the PSO model best described our absorption process, and also best described our absorption process for FeACF. So looking at our data for our adsorbents, what we first did was to find our experimental capacity of our adsorbent. So these were what we calculated at the end of our experiment. And since we've also determined that the PFO model didn't fit our data well, and we think the PSO fits our data, we are going with the PSO model. And the reason we want to go with the PSO model is because the capacities generated by our PSO model was closer to our experimental capacities compared to that of our PFO model. So for example, biochar had an experimental capacity of 1.15, and the PSO model gave us a capacity of 1.30. We had a capacity of 4.15 experimentally, and the PFO model gave us a capacity of 4.10. This is just to confirm that indeed the PSO model best fits our data. So in terms of the adsorption kinetics, in terms of how fast adsorbents can remove acinates from water, our K constant, which is our pseudo-second rate, our rate constant, tells us that GAC removed has the fastest kinetics, followed by AB, BC, and then ACF. For our ion modified adsorbents, we also have a similar situation whereby experimental capacity was very close to our PSO capacity from our model. So we do indeed confirm the PSO model best describes our kinetic process. And for our adsorbents, we can see biochar having the fastest kinetics here. And this very fast kinetics could be attributed to the fact that the ion on biochar was formed outside the macroporous region, signifying that so long as we had our adsorbent in there, the first thing acinate saw was the ion in our solution. So that led to this fastest kinetics. GAC's rate reduced after ion modification, and this also signifies that some of the pores were interfering with the acinate removal. ACF, on the other hand, had the same rate constant between the ion modified and the raw material. And this also signifies that even though we had pore blockage, ACF had a wide, because ACF had broad, it had its fibrous forms, it was evenly distributed in our water, hence attracting acinate ions. So for our absorption capacity, for our unmodified adsorbents, we have our equilibrium concentration on our x-axis, and we have our capacity on our y-axis. So starting with biochar, which is characterized by black data points, the blue is our Freundlich model, the red is our Langmuir model. We can see that there was an overlap between both models. We also had an overlap between the models for AB. However, for GAC and ACF, we're trying to find out which model best fits, but it seems like they were all close. And for our ion modified adsorbents, we can see that Fe biochar had both models overlapping. We also had similar thing for FEAB as well as GAC and ACF. So what we did was to pull out the data to compare them side by side. First and foremost, one thing we observed was the capacity of our adsorbents. So after ion modification, before ion modification, biochar had a capacity of 0.8, followed by AB, GAC, and ACF. And looking at our models, for our Freundlich model and our Langmuir model, we decided to use the R square to eliminate the preferable model. In as much as both models did describe the adsorption process, because our adsorbents have heterogeneous surfaces, we think the Freundlich model would best describe our absorption process. So for going with the Freundlich model, we can see our N values here, which is our this N is our dimensionless constant. Yes, that's our dimensionless constant. And research also shows that having an N value between 1 and 10 signifies that we have a favorable adsorption. So for GAC and ACF, we can see that our N value is between 1 and 10. So the adsorption process was favorable here. For BC, our adsorption process was not favorable. However, after ion modification, we can see an improvement in our capacities. Fe biochar had the lowest capacity, followed by FEAB, FEGAC, and FEACF. And also looking at both models, we can see that after ion modification, our R-square values increased in a little bit, especially for our AB and BC adsorbents. However, we still decided to go with the Freundlich model because it had a higher R-square than the Langmuir model. And we also know that our adsorbents have a heterogeneous surface, so the Freundlich model indeed describes the surface characteristics of our adsorbents. Looking at our N constants for Fe, our ion modified adsorbents, we can see that they are all between 1 and 10, signifying that our adsorption process was favorable. Also looking at our Freundlich K, we can also see that our K values was increasing in this order with the adsorbent, signifying increasing adsorption capacities as well. So putting our graphs side by side, wanted to see how much acylate could be absorbed with our ion modified and our raw adsorbents. So on our x-axis, we have our adsorbents and we have our capacities on our y-axis. And we can see that after ion modification, the capacities of all our materials improved. So in conclusion, the order for our acylate removal was in the order ACF, GAC, BC, and AB respectively. And secondly, the surface area of activated biochar stayed the same even after ion modification. And that could mean that the ion precipitate was formed outside our macroporous region. One key thing to also take note is that the ion modification acted as a chemical activation agent for our BC, thereby increasing its surface area by 128%. And we also saw a decrease in the surface area for GAC and ACF by 15% and 8% respectively. And this confirms that ion precipitates were successfully hosted within the pores of our material, causing pore blockage. After ion modification, the acylate removal performance increased across all our adsorbents, with FEACF having a 25% increase, FEGAC has a 126% increase, FEAB had a 262% increase, followed by BC with an 80% increase. Negligible ion leaching was also confirmed, and that means that our precipitates were successfully anchored onto our adsorbents, and that also prevented any secondary form of contamination. One thing we also noted was that the felt form, which is our ACF, provided continuous high capacity rather than granular active forms, and this could also be due to its accessible fibrous morphology in water. So in conclusion, we can say that acid digestion and our stability test proved that iron was not only present but was also securely anchored onto our adsorbent surface. Secondly, we're also successfully able to map the porosity, surface area, pore size distribution, and surface charge of all our adsorbents. Our baseline studies confirmed that our unmodified adsorbent had limited affinity for arsenate, highlighting the need for modification. And finally, we also confirmed that ion modification drastically enhanced arsenate removal across all our adsorbents. So here are some future recommendations. We carried out our experiment using 10 millimolar KCl to mimic stormwater. However, in real stormwater, we have coexisting ions such as phosphorus, which hinders the absorption of arsenate. So we have to in future evaluate the performance of our absorbents in stormwater containing these coexisting ions. Secondly, we can also conduct flow-through column experiments to find out how to scale up our experiment from a batch adsorption in the lab to practical applications. We can also explore possible regeneration methods to find out how many times you can use our materials before they get exhausted. And finally, we have to explore safe ways to dispose our adsorbents so that we do not introduce any form of secondary contamination. Here are some of the references I used, and these are some of my contributions throughout my graduate study here at South. Before I wrap up, I want to say a very big thank you to Dr. Onat, to Dr. V, to Dr. Shao, to my wife, to my friends and family here for your support. Thank you very much.